my name's Ivan Straznicky. I'm the CTO for Advanced Packaging at Curtiss-Wright Defense Solutions. We're going to be talking about today for 20 minutes or less, high-speed signal integrity in the context of VPX modules, systems, and backplanes. And if you remember from last year, those of you who were here last year, I gave a similar presentation. And last year the theme was hoodoo voodoo, and it was a great analogy for high-speed signal integrity. This year, with the Big Texas theme, I'm calling this a big deal. The reason for that is because Mike Walmsley stole a little bit of my thunder, which I had worked into my presentation already. That's why I had to have him up here, just so my presentation would go relatively smoothly. But we're announcing jointly that VPX is now capable of supporting Gen 5 protocols, specifically 100 gigabit Ethernet, and even more specifically 100 gig KR4 for those of you who that means something to. This is again from last year. This is the VPX transmission channel for those of you who are familiar with it. It's relatively straightforward. You've got a transmitting chip on a TX module. You have a receiving chip on an RX module. Two pairs of mated VPX connectors in between, as well as a backplane. Now, each couple of measures of goodness of this channel for it to operate properly. One is called BER, or bit error rate, and the other one is called an eye opening. And with the eye opening, the specific requirement, and this is going back to Gen 4 actually. With Gen 5, there are some different requirements that I'll talk about in subsequent slides. But with Gen 4, there was a pretty firm requirement to have a 15 millivolt eye height and something called 0.3 UI, or unit interval eye width, to meet the channel requirements. The bit error rate is, again, for those of you who are familiar with the channel requirements, there's a pretty firm requirement to at least have something called a 10 to the minus 12 bit error rate. And that's really a measure of the numbers of bit errors per unit time. Pretty simple calculation. You measure for a unit time how many bit errors you get, and you look at the total number of bits transmitted, divide that, and that's your bit error rate. So that all sounds relatively straightforward. Our bosses might ask us, what's the big deal? Just make it work, right? Well, it's obviously not how it works. With the different elements in the transmission channel, things like the VGAs that are transmitting and receiving, the printed circuit boards, the mated connectors, the backplanes, etc. Each part of the transmission channel has unique electrical characteristics that serve to impede, slow down, jumble the transmitted signal. So specifically things like insertion losses, return losses. With VPX, with the data plane where you're transmitting across a bunch of lanes in more or less parallel, crosstalk is a huge issue. And all of those are caused by even deeper phenomena, things like parasitic inductances and capacitances, et cetera, et cetera. I won't bore you with all of the science, but in particular, one of the important aspects as you go up higher and higher in speed is something called weave skew, where when you run differential pairs on copper over FR4, when you take an X-ray photo of that FR4, it looks like that image that I'm showing, where you've got glass bundles underneath mixed with resin, and where your differential pair lines up on those, you can see it's not a uniform mix, you will get skew. You'll get a delay in either the positive or the negative leg of the differential pair, and that causes problems with your signal transmission. That's not something we had to worry about in earlier generations, but with Gen 4 or Gen 5 in the future, it's a critical part of managing the data transmission channel. So since this is supposed to be a TED Talk format, how am I doing so far, Jerry?
You're good. Just
not
talk
bad?
Louder.
Talk louder? Well, that's a first. Move it up a little bit higher. Okay. How's that? Is that any better? Okay. So this is a TED Talk format presentations that we're giving here. Last year when I talked about good versus bad signal integrity, I showed a couple of sports car tracks, but with with autonomous driving right around the corner. I'm going to make this a little more human. So here goes good eye, bad eye. So VPX, this is kind of the next few slides are going to be the story of VPX in, let's say, 5 or so slides with respect to the serial fabrics and protocols that were the basis of why VPX came into existence. You know, we had parallel buses before. Michael was talking about that earlier. Now we have a bunch of serial fabrics and protocols, an explosion of them, really. VPX Gen 1, when we started way back in around 2005, back then, the serial fabrics were running at about 2.5 to 3.125 gigabaud. The advertised limit of the VPX connector in the channel at that time was 6.25 gigabaud, so we were good to go. And sure enough, we breezed through Gen 1 more or less readily, I would say, relatively speaking. Gen 2 at 5 to 6.25 gigabaud, we were now at the advertised limit of the connector in the channel, but we were still able to get through, without relatively unscathed, I would say. With Gen 3, things at the time posed a relatively big hurdle. We were significantly beyond the advertised rated signal speed of the connector in the channel. However, based with a number of OEMs, Curtiss-Wright included, have met the challenge. Some of the specific challenges that we had at the time were things like return losses and a pretty obscure parameter known as ICR, or insertion loss to crosstalk ratio, which is a requirement of the 40 gig, 10 gig KR Ethernet standards. But we met the challenge. We were able to overcome that with some smart design rules, et cetera. And Curtiss-Wright and others now have product out there for several years. Curtiss-Wright's offering is called Fabric 40, but there are other vendors that have product suites out there as well. So last year, Curtiss-Wright at Embedded Tech Trends talked about Gen 4 VPX, specifically PCI Express 4.0. And we announced that we were capable of supporting those speeds on the standard VPX connector, not with Hoodoo Voodoo as I've left here from last year, but with some advanced design rules and features. And we've been moving forward since then. So now we hit 2018 and the emergence of Gen 5 protocols, specifically the 100 gig KR4 that I was mentioning earlier that runs at 25.8 gigabaud. There's a big question, or has been a big question, over whether or not this could work over VPX. The bit error rate and the eye-opening requirements, at what point would they fail? And would we be able to implement enough improvements in each of those elements of that channel to make them pass ultimately? Before I answer that question, I'd like to have you visualize that channel that we saw earlier. And given that I'm a mechanical engineer, I like to use mechanical analogies. Each one of those elements, so the printed circuit boards, the mated connectors, the backplane, et cetera, each one of those has what I like to call knobs to turn or levers to adjust. And what I mean by that is you can work within the boundaries of reliability and fabrication and manufacturability to improve each one of those. And if you do it smartly in such a way that you look at what the entire channel does, you can get some pretty impressive results. And specifically, moving it back to the electrical realm, so specifically you have things like insertion losses, return losses, you have things like laminate material choices that you can play with, you have things like trace geometries and lengths, and some of the more subtle things like the weave skew that I mentioned, as well as trace surface roughness. I could go on and on and on, and each one of those, that list of what might be considered as issues and things you have to pay attention to, offers an opportunity for improvement. So if you look at those and you play around with them, you can create a channel that works. So all that being said, basically I'd like to re-announce that we're capable of supporting Gen 5 on VPX with both the standard and the new connector that Mike announced, the RT3. There are some limited cases where you can use the old connector. I'll talk about that in a subsequent slide. But if you want to open up the horizon to everything, things like 20-inch backplanes, et cetera, likely the RT3 is required. So that was pretty easy to say, wasn't it? Gen 5 VPX is here. Ta-da! No? Okay. Yeah, you guys saw the slide, that's why, right? It was easy to say, but not so easy to prove to our customers and to ourselves. In particular, when you start doing simulations and you start looking at, again, knobs you can turn, levers you can adjust, you really need to pay attention to what kinds of assumptions you're making. And what we've done here to prove it to ourselves and to you and ultimately to our customers is these are just some of the assumptions that we've made to show you how conservative we've been. We used real-world trace geometries on both the modules and the backplanes, real-world via lengths and stub lengths. That weave skew I was talking about. We have some pretty recent data showing what it might be on the module and the backplane side. So we used a total of 15 picoseconds. Off nominal impedances, you've got your impedances are nominal, and then there's plus or minus 10%, right, for all you EEs. That's a pretty wide range. You don't necessarily need to go to that plus or minus 10% because that might not be realistic, but you need to do things like RSS modeling, et cetera, to get a good, a reasonable and a reasonably conservative number for impedance. Interesting thing about the worst case differential pairs. Gen 4 we had one pair that was the worst. Gen 5 we had a different pair that was worst. I'm not going to tell you which one because we spent 2 years figuring this out. Then you have to model all the crosstalk. I mentioned how important crosstalk is for VPX and how much a part to play it has. We've also found we had two separate groups, independent groups actually, doing modeling. And we found out that even with all the work that we did to try to make them consistent, we ended up getting up to a half a dB of difference between those two groups for the simulations. That resulted in what, and I'll show you the next slide, in us bumping up our margin requirement by half a dB. Causality correction is something you need to do as well. The last one is a little bit of good news at the end of the day. With the 100 gig KR4 Ethernet has something called Reed-Solomon forward error correction enabled in the channel. That allows you to increase have a pretty degraded channel and bump up your transmission capability, several orders of magnitude. So that's a bit of a saving grace within 100 gig KR4. Before I dive into this, is a bit of an eye chart. My apologies for that. That's so much for the TED Talk format. Basically, with all the work that we did, we were finally able to come up with some passing results, and it did take a lot of work. These first two, in this table, these first two rows are basically something that emulate 3U VPX systems, a longer 14 slot versus a somewhat shorter 12 slot. You can see the corresponding backplane trace lengths. With those, with the RT2R connector, the VPX RT2R connector, we were able to make those work above the 3.5 dB comm margin, which I just talked about in the previous slide, where we bumped it up. The original requirement from IEEE is 3 dB, but we bumped it up by half a dB. You can see we pass all of those requirements for both BGA sizes in comm, which are 12 millimeter and 30 millimeter. That's what those case 1 and case 2 columns are. Once you start to get into bigger systems like 6U, some of the HPEC systems, you need to start looking at the RT3 because for you can see we got some decent results, but even that first one we were pretty close to the 3.5 dB with the RT3. With the RT2R, that would not have worked. So these are kind of a smattering of, we've probably got 3 times or more of this number of cases that we've done, but these are some very specific ones that I pulled out that I thought are good representations of some system possibilities out there from things like OpenVPX. So that was Gen 5 VPX. The obvious question is, what's the next big thing, or what's next? There are some, Gen 4, it was pretty clear what was next. It was PCI Express 4.0. Gen 5, it was pretty clear what was next. It was 100 gig KR4. Next gen, Gen 6, etc. There isn't really a clear fabric or protocol that looks like it's going to be a gimme for the next future implementation. There is Gen 5, just to add to to make things a little confusing, there is Gen 5 PCI Express, which runs at 32 gigabaud. That is a firm possibility for being able to do with the advanced design rules that we have, as well as the RT3 connector. That's Whole lot of work to make sure that that's the case. It might take another year before I come back here and say, yeah, we can do that. But really, there isn't anything clear, so that's why I've left it as FabricX. There's a bunch of testing that needs to be done as well before we design and introduce new products, which is going to be in the realm of the next 2 years. There's a bunch of testing that's required. We have some pretty good confidence based on all the conservative assumptions that we made that we're going to be able to get there, but the devil's in the details. Once you start designing actual products, there's a lot of things that change, and that could make some changes to the potentially relatively simplistic channels that we've modeled. But at the end of the day, we think in the next 2 years, there's going to be a good bow wave of Fabric 100 products. So that leaves FabricX for the future.